In this section, we'll see how blockchains actually earn our trust. We'll walk through blocks, hashes, Merkle trees, and consensus, how nodes agree on a single history, and how any tampering becomes immediately obvious. These mechanics form the technical backbone of verifiable trust. Historically, we trusted institutions, brands, and people based on reputation and relationships. In a post-AI world, that's no longer enough. Deepfakes and automated attacks make it trivial to fake identities, logs, and even entire histories. Cryptographic trust flips the model. Instead of trust who you know, we rely on proofs, protocols, and consensus that anyone can independently verify. A block really has two jobs: sealing the past and packaging new data. The header is the seal. It stores metadata, a timestamp, a nonce for consensus, and, crucially, the hash of the previous block. That single hash links history into a tamper-evident chain. The body is the payload, transactions. Their hashes are combined into a Merkle root, which is committed into the header. Change any transaction, and the root changes, so the seal no longer verifies. Hashing is what makes a blockchain's history tamper-evident. A hash function is deterministic. The same block data always produces the same hash. It also has an avalanche effect. Flip a single bit in a transaction, and the hash changes dramatically. Because each block stores the hash of the previous block, editing one block breaks the hash of every block after it. To rewrite history, an attacker would have to recompute and get the network to accept all subsequent blocks. Merkle trees let blockchains compress truth about many transactions into one short hash. Each leaf is the hash of a transaction. Pairs of hashes are combined and rehashed layer by layer until we reach a single root. If any transaction changes, its hash changes, that difference propagates up the tree, and the Merkle root is different. This structure lets a node prove a specific transaction is in a block using only a tiny Merkle proof, not the entire dataset. Merkle proofs give us scalable auditability without moving huge amounts of data. Instead of downloading every transaction, a verifier only needs the Merkle root and a short path of sibling hashes. With that path, they recompute the root locally. If it matches the chain's root, that transaction is guaranteed to be part of the committed block. Because proof size grows only logarithmically with data, blockchains can be globally replicated yet still efficiently auditable. Consensus is the process by which the network agrees on a single history, even when some nodes fail or misbehave. We usually plan for two kinds of failures: nodes that simply disappear, and nodes that actively lie or send conflicting messages. The design goal is to maintain two core properties: safety, meaning no conflicting histories, and liveness, meaning the system keeps making progress. Proof of work turns security into a question of physics and money. To rewrite history, an attacker must burn at least as much energy and hardware as the honest network, and sustain that over time. A cryptographic difficulty target converts raw hash power into a probabilistic lottery, making blocks expensive to produce but easy to verify. This yields strong decentralized security, but with high energy cost, environmental impact, and relatively low throughput. Proof of stake ties security directly to the cost of capital. Validators lock up real value, and that stake becomes an economic bond backing honest behavior. To attack the system, you must control and risk a huge amount of capital, which makes large-scale attacks expensive. If a validator cheats, slashing destroys part of that stake. The trade-off is that wealthy participants can dominate, so POS designs have to counter centralization and long-range attack risks. Byzantine fault-tolerant consensus is the workhorse for many permissioned enterprise blockchains. Instead of mining, nodes explicitly vote across multiple rounds: pre-prepare, prepare, then commit, to agree on each block. Once enough votes are collected, the decision is final immediately. There's no probability of reorgs. The catch is participation. You need a known, semi-trusted validator set, like a consortium. In return, you give up open participation for predictable performance and instant, auditable finality. Choosing a consensus mechanism is really about choosing which risks you're willing to accept. Proof of work tends to maximize decentralization and credible neutrality, but you pay in energy use and slower finality. Proof of stake improves energy efficiency and scalability, while tightening economic and governance assumptions. BFT-style protocols give extremely fast finality and high throughput, but only if you trust a relatively small known validator set. Your threat model and participant trust levels should drive this trade-off, not fashion. Public or permissionless chains maximize openness. Anyone can join, identities are often pseudonymous, and censorship resistance is strong. That's ideal for open innovation and neutral infrastructure, but governance and compliance are harder, and performance can be limited. Permission chains reverse those trade-offs. Participants are vetted, access is gated, and you can enforce regulatory requirements and higher throughput. The cost is more central control and weaker guarantees against censorship. Modern regulations often demand two things at once: strong privacy and strong transparency. Blockchains excel at transparency, but they're terrible at forgetting data or hiding it once published. Zero-knowledge proofs bridge this gap. You keep raw attributes, like your birth date, completely private. A proof circuit checks a rule, such as age is over 18, and outputs only true or false. Auditors and smart contracts get verifiable answers without ever touching the underlying personal data. Hybrid architectures are about placing different levels of trust in the right layers. The base ledger is your trust anchor. It handles settlement, immutability, and the strongest security guarantees. Above that, off-chain and Layer 2 components handle most of the computation, efficiency work, and privacy. They send succinct proofs or commitments down and inherit security back up. The key risk is the Oracle problem. Any bridge that brings external data into smart contracts becomes a critical trust bottleneck. Strategic design for verifiable trust means you don't just pick a blockchain or a crypto primitive. You engineer how architecture, consensus, and data structures work together as a single, auditable system. In a post-AI, post-quantum world, you mitigate risk by encoding trust into transparent, upgradable protocols instead of depending on individual operators or institutions.